Let's see how well we remembered our measurements from last week. So taking a look here, 33 yards, converting that into rods. Now, if you recall, the strategy we used for converting is we set it up as a fraction. So 33 yards over 1. And then when we set up our conversion factor here, our unity fraction, how do we know what to put on bottom? Well, whatever unit we're getting rid of has to cross cancel. So it has to be yards down here, so it'll cross cancel with the yards. So this is going to have to be rods. Now that we know what units go where, then we can look for the relationship between those units. And the relationship between them would be 1 rod is 5.5 yards. So this is saying the yards are gone. 33 times 1 rod is 33 rods. Over 1 times 5.5 is 5.5. And then you divide out. 33 divided by 5.5 is 6. So 33 yards is 6 rods. This next one here, 4 gallons going into pints. We put 4 gallons up there and put it over 1. As we go to convert it into something else, we have to put gallons on bottom so that they'll cancel out. But we don't have a direct conversion from gallons to pints. We have a conversion from gallons to quarts. So let's put that in there. 1 gallon is 4 quarts. So now the gallons have canceled out. But we don't want quarts, we want pints. We're going to put quarts on bottom so that they cancel out, and pints on top. And we know that 1 quart is 2 pints. So now we have 4 times 4 is 16, times 2 pints is 32 pints. And on bottom we have 1 times 1 times 1, which is just 1. So that is 32 pints. For the next one here, 192 ounces. Again, we put that over 1. Getting rid of ounces, so ounces go on bottom, so they cancel out. Pounds on top, and we know that 1 pound is 16 ounces. So as we multiply here, 192 times 1 pound is 192 pounds. 1 times 16 is 16, so we're going to have to divide. 192 divided by 16 is 12 pounds. For our metric units, it's just a matter of moving the decimal point. Remember, we have our chart where we have the main unit in the middle here. So you got meters, grams, or liters are in the middle. Then this is deci, centi, milli. Going this way is deca, hecto, and kilo. So if we have 5.34 meters, that's right here. We're converting to centimeters, which would be right here. To get from meters to centimeters, we're moving 2 spots to the right, which means to make that conversion, our decimal point has to move 2 spots to the right. So it's 534 centimeters. Same up here for grams to milligrams, going from grams to milligrams. Grams is right here, milligrams would be here. That is 1, 2, 3 spots to the right. Now there's no decimal point here, so we have to put it at the end, and we move 1, 2, 3 spots to the right, giving us 270,000 milligrams. And then this one here, milliliters to centiliters. Well, here's milli, and we're going to centi. To get from milli to centi, that's 1 spot to the left. So my decimal point goes 1 spot to the left. So that's going to be 0.48 centiliters. Any questions on those conversions? So now the part that may have popped up in the homework that we did not get to last Thursday is converting from metric to standard or standard to metric. Now when I do these conversions, I only have 1 conversion memorized for each type of measurement: length, capacity, and mass and weight. Before we get into it too much, I want to talk a little bit about that. I said mass and weight there. In standard measurement, we tend to measure weight. In metric measurement, we tend to measure mass. There is a difference between them, only we tend to use them interchangeably in common practice. If you got onto the engineering side of things where you had to be a little more precise with stuff, that won't work so well. But let's take a look at what is the difference. What most of us are used to measuring is weight. Weight is a measurement of force. It is technically the force that gravity pulls on an object with. So it's the force of gravity. And the way weight is measured is with a spring. So you'll take a spring here. Do that very poorly, but that's okay. And you put some sort of a measuring device on that spring, which is called a scale. That's why it's called a scale. And you'll have an indicator here that's at 0 or whatever. And then you put your weight on it, and your weight causes it to stretch down, and as it stretches, that indicator moves, and it slides down. So the distance that spring stretches is measured by the movement of that indicator, which gives you the weight. Mass is slightly different. Mass is the amount of matter in an object. Now, we can't take an object apart and count the number of atoms in it. So to measure mass, we use something, this is called a scale. To measure mass, we use something called a balance. What a balance does, it's kind of like a teeter-totter. You put a known mass on one side, then you put the object we're trying to measure on the other side, and see if it balances. If it doesn't balance, you take away pieces from the known mass or add pieces to the known mass until it does balance. And whatever known mass balances it, that's what the mass of that object is. Now you might be sitting here looking at it and saying, well, what's the big deal? Why is there a difference? Well, if we go to the moon, where there's 1/6 the amount of gravity there is on Earth, this scale isn't going to stretch near as much. It's going to stretch 1/6 the amount because gravity is less. However, on the moon, the mass will not change because gravity will pull less on this, but it's also going to pull less on our known mass. So the exact same known mass will balance it. So mass is independent of gravity. On Earth, we tend to use the two interchangeably because gravity is relatively constant on Earth. It's actually a little bit stronger at the North and South Pole and a little bit weaker right at the equator. But it's close enough to the same that if you know the mass, you pretty much know the weight of an object. So we use them interchangeably. But just be aware that when we're talking about grams and kilograms and stuff for metric units, what we're really talking about there is mass. And when we're talking about pounds and ounces in our standard units, that is talking about weight. There is a standard unit of mass. You don't need to write this down because it's never going to appear on a test. Unless you were to go into like mechanical design or some form of engineering, it would never come up. But the unit of mass in the standard system is something called a slug. One slug is 16 pounds. And in the metric system, there is a unit of weight. It's called a newton. 1 kilogram is 9.8 newtons in size. Again, I just wanted to point that out so that you knew that there was a difference. We will convert from pounds to kilograms even though technically one's weight and one's mass, just because on Earth mass and weight are pretty much can be interchanged without too much error. So anyway, let's look now at converting some of our units from standard to metric or the other way around. We'll start out with length. As I mentioned, I only have memorized one conversion for each type of measurement. For length, the one conversion I have memorized is 1 inch equals 2.54 centimeters. This one is actually relatively exact. It's not perfect, but it is really, really close. In fact, I believe your book calls it an exact value. So if I want to convert from inches to centimeters or centimeters to inches, let's say I have 4 inches and I want to know how many centimeters that is. Well, I'm going to set that up just like I have any of the others. 4 inches over 1 times what has to go on bottom and what has to go on top in this conversion. What goes on bottom? Inches, so they'll cancel out. So on top it'll be centimeters. That's what I'm going to. My relationship is 1 inch, so this is 1 inch on bottom, equals 2.54 centimeters. So now the inches cancel out. 4 times 2.54 is 10.16 centimeters. Now I purposely chose that problem so it worked the way the textbook wanted it to. To me, even if I was going from centimeters into inches, I would still use that conversion. If I was doing like, well, let's say I have 32 centimeters, and I want to know how many inches that is, I would use that same conversion. It would just be upside down. I would do 32 centimeters. Then in my conversion factor, centimeters are going to go on bottom, inches on top, and I would do 1 inch and 2.54 centimeters. Centimeters cancel out. I've got 32 on top here, 32 inches. 32 times 1 inch is 32 inches. And on bottom, 1 times 2.54 is 2.54. And since the numerator or the denominator is not 1, I have to divide that out. So then I would have to do 32 divided by 2.54, which would give me 12.598 inches. Depending on how it asks to have that rounded, that might end up being, if they want to go to the nearest hundredth of an inch, how would I round that? Because this is the hundredth, that's saying round up, but I'm at a 9, so it has to be 12.60. Very good. The textbook, however, does not want you using conversion factors that have anything other than 1 in the denominator. So the way the textbook would want you to do this would look like this. Start out with the 32 centimeters over 1. But in our conversion factor, they want this not only to be centimeters on bottom, but to be 1 centimeter on bottom. Always a 1 in the bottom of that conversion fraction, that unity fraction. If you look in your textbook on page 576, there is a table of metric to standard conversion factors, equivalencies. In that table, you'll see the left side is labeled US to metric. The right side is labeled metric to US. We are going from metric to standard, or metric to US here, so we'd be using that right side, metric to US. And we see there 1 centimeter is listed as being 0.394 inches. So this would be the conversion factor the textbook would want us to use because it has 1 in the denominator. So we're not dividing by anything. We're always multiplying. This is the way the textbook wants it done. This is the way it's going to do it in my math lab too, by the way. I think I warned you on Thursday of that it doesn't want you to divide. It always wants you multiplying. So it wants a 1 as your denominator. So then we would do 32 times 12.394, which gives us 12.608. Now, if we're rounding to the nearest hundredth, this one's going to become 12.61. Doesn't mean we did one of them wrong, it's just round off errors and the conversion factors. When we're going from metric to standard or the other way around, none of these conversion factors are perfect, except for the 2.54 is very, very, very nearly perfect. They're all rounded off. So there's going to be some slop. Well, which conversion factor you choose determines just how much slop there's going to be. You can tell this one was slightly different than this one. The problem is if you entered this one in my math lab, it would most likely mark it wrong. So let's look at weight. Well, weight to mass, I should say. So when we're looking at weight, the one conversion that I have memorized is that 1 kilogram is equal to 2.2 pounds. And again, I shouldn't say equal, it's approximately. Should have the little curvy equal sign instead of the absolute equal sign. Because they're not absolutely equal, they're approximately equal. Technically it's like 2.208 pounds or something like that if you wanted to get into more precise. Depending on the application, you do need to be sometimes more or less precise. But again, this only works if I'm going from metric to standard. If somebody tells you that they have something that weighs 60 kilos, 60 kilograms, you need to know how many pounds that is to see if you can lift it. Well, 60 kilograms over 1. And our conversion factor, what's going to go on bottom? Kilograms. And of course, we know the textbook wants us to have 1 kilogram down there. So yes, 1 kilogram is 2.2 pounds. So the kilograms cancel out, and you have 60 times 2.2 is 132 pounds. If you're going the other way from pounds to kilograms, I normally would just do the opposite. I would just divide by 2.2 instead of multiply. But again, the textbook wants you using 1 in those denominators. So let's say that you weigh 160 pounds and you want to know how much that's going to be in kilograms. Well, you got your 160 pounds over 1. 1 pound is going to go on bottom. If we look in our book on page 576, now in my math lab, it'll actually bring up a little chart. At the bottom of the question, there'll be a little button that looks kind of like that. If you click on that, it'll actually bring up your conversion chart, so you don't have to have your textbook out. You can just look it up right there. So anyway, in the book here, 1 pound is 0.454 kilograms. So the pounds cancel out. We have 160 times 0.454. Is 72.64 kilograms. Now again, the way I would have done that is I'd have just done the 160, and I would put 1 kilogram as 2.2 pounds. And I would ended up dividing by the 2.2 instead of multiplying by 0.454. You realize you get pretty much the same thing. You can see a little bit of a round off error again. 72.73 instead of 72.64. Let's look now at capacity. So capacity is our gallons and liters. When it comes to capacity, the one that I have memorized is that 1 gallon is approximately 3.785 liters. Actually, I believe your textbook uses just 3.79, so I'm going to round it back to that. 3.785 is the one I've always used. It's like 3.7856 or something like that. So it does round to 3.79 if they're going just 2 digits. So again, this is our standard to metric conversion. Let's say that we have an 18-gallon tank in our car, and we want to know how many liters that would be if we were going to fill up our gas tank in liters. So 18 gallons over 1. Over here we put gallons on bottom, 1 gallon, and 3.79 liters on top. The gallons cancel out. We have 18 times 3.79, 68.22. So that's 68.22 liters. Well, let's take another look at another one here. Let's say that we have something that is, make sure I've got one that we have here. 5 quarts. We want to go into liters. So I've got my 5 quarts over 1. In my conversion factor, quarts are going to go on bottom, and I'm going to want it to be 1 quart. So I look, do I have a conversion of 1 quart equals something in liters? If I look there, I get 1 quart is 0.946. Everybody see where that comes from? So again, my quarts will cross cancel. It's 5 times 0.946. Giving us 4.73 liters. If I wanted to go the other way, let's say that we are told that we have something that is 400 milliliters. And we want to know how many pints that is. We look in our table in the book on page 576, and we have absolutely nothing that equates milliliters to pints. All we have is liters to gallons or liters to quarts. So what that means is the first thing we have to do is turn milliliters into liters. Well, to get from 400 milliliters to liters, we go back to looking at that chart. Liters are in the center, then it is deciliters, centiliters, and milliliters. So to go from milliliters to liters, it's 1, 2, 3 spots to the left. So my decimal point has to go 1, 2, 3 spots to the left. This is 0.4 liters. I'm going to put that over 1 and set up a conversion factor with 1 liter on bottom. Now I have 1 liter, can either go to gallons or it can go to quarts. Which one is closer to pints? Gallons or quarts? Quarts are, right? So we're going to look at 1 liter is 1.06 quarts. So liter is going to cancel out. 0.4 times 1.06 is 0.424 quarts over 1. So it's just 0.424 quarts. Now I need to convert that into pints. So my quarts go on bottom. 1 quart is 2 pints. The quarts cancel out. 0.424 times 2 is 0.848 pints. So 400 milliliters is 0.848 pints. Any questions? one unit that we have not talked about yet, because there isn't multiple units within each system, is temperature. But we do want to look at converting between systems with temperature. Temperature, however, is unique because it doesn't involve just a simple conversion factor. To convert temperatures, we have to use a formula. And let me show you why. Standard temperature uses something called the Fahrenheit scale. That doesn't look right. I must have missed something, but close enough. And then metric temperature is in Celsius scale. And both scales use two benchmarks. One of them is when water boils or condenses, and the other is when water freezes or thaws. In the Fahrenheit scale, what temperature does water freeze? 32 degrees Fahrenheit. Very good. So as it's getting colder at 32 degrees Fahrenheit, water will freeze. Or if it's going the other way, when you get up to 32 degrees Fahrenheit, ice will thaw. In the Fahrenheit scale, what temperature does water boil? Anybody? At standard atmospheric pressure, it boils at 212 degrees Fahrenheit. So, water will turn to steam at 212 degrees, or the other side of that is steam will condense back into water at 212 degrees. On the Celsius scale, what temperature does water freeze? Zero degrees Celsius, water will freeze, ice will thaw. Anybody know what temperature water boils at? There you go. 100 degrees Celsius is where water boils in the Fahrenheit or in the Celsius scale. So you can see a little bit simpler in the metric scale there, 0 and 100. At one point, they actually started calling Celsius the centigrade scale. Centi means 100, grade means division. It's because it's in 100 divisions. They called it centigrade. You still hear that every now and then. They'll say something that's 32 degrees centigrade, that's 30 degrees Celsius. Now, a couple of things you will notice here. One is, on the Fahrenheit scale, from freezing to thawing, that is 180 degree range. On the Celsius scale, it is only a 100 degree range, which is telling me that the 1 degree Fahrenheit is a smaller change in temperature than 1 degree Celsius is. Now, the other thing that you'll notice, and this is one of the big things, is this is the only type of measurement we have that does not have a common 0 point. Water freezes at 0 Celsius, but that is not 0 Fahrenheit. In every other type of measurement and conversion we've done, there's a 0 point. 0 inches is equal to 0 centimeters. 0 gallons is equal to 0 liters. 0 pounds is 0 kilograms. There's a common 0 point. That is why we can just do that simple conversion factor. Here we do not have a 0 point, so we cannot use a conversion factor. We have to use a formula. So to convert from Celsius going into Fahrenheit, our Fahrenheit temperature is going to equal 9/5 times our Celsius temperature plus 32. So if we are told, you listen to the news, maybe you're going to Europe or someplace that's on the metric system, And they say that the temperature is going to be 28 degrees Celsius today. Sounds kind of chilly by our standards, doesn't it? If they said 28 degrees in Wisconsin, you'd be putting on your coat. Well, what is that in degrees Fahrenheit? Well, we replaced the C in our formula with 28. So now I'm going to go ahead and just punch this in the calculator. And the way I'm going to do that, 9/5, I'm just do is 9 divided by 5 because I don't have fractions on this calculator. Then times C, so it's times 28, and plus 32 is 82.4 degrees Fahrenheit. That's a warm enough day for me. On the other side of things, if I want to go from Fahrenheit into Celsius, my Celsius temperature is equal to 5/9 times, I have to subtract 32 from the Fahrenheit temperature first. So the example I like to use here, just because I teach this a lot to my medical students, human body temperature is considered to be 98.6 degrees Fahrenheit. Let's convert that into degrees Celsius. So I put the 98.6 in for F. What's the first thing I have to do here? In the parentheses, you got it. So I have to do the 98.6 minus 32 is 66.6. Then what? Now the parentheses are reduced to a single number, so I can do the 5/9 times 66.6. Again, I could treat that as 5 divided by 9 and then times 66.6. Comes out to be 37 degrees. So human body temperature is 37 degrees Celsius. Any questions? So, a really, really cold winter day around here. It's negative 40 degrees Fahrenheit. In your notes, figure out for me what that's going to be in degrees Celsius. This is one of those where when most people set it up, they punch it in their calculator and they think they must have done something wrong. And they didn't. It's just me thinking I'm funny. So you punch this in 5/9, so 5 divided by 9. Oops, screw that up. 5 divided by 9 times, in my parentheses, negative 40 minus 32. Hate equals, and I get negative 40. Negative 40 is the one temperature that's exactly the same on both scales. So negative 40 degrees Fahrenheit should come out to be negative 40 degrees Celsius. How many of you got that one to come out? Okay. So now what if we're dealing with a little bit different units? Let's say, well, let's use this example. If I were to tell you guys that I can throw a baseball at a speed of 90 feet per second, would you believe me? You're all sitting there thinking, oh, we don't want to tell him no. We don't want to upset him. Well, if you think about that on a baseball field, that would be standing at first base, throwing the ball to home plate, and it gets there in 1 second. The question is that fast? Well, what are we used to seeing speeds measured in? Miles per hour. We know that if that's miles, if that were 90 miles per hour, that's a major league fastball. There's a reason I'm sitting in front of you and not in the major leagues. So how would we convert from 90 feet per second into miles per hour? Well, let's take a look. First thing we have to do, we talked about this when we talked about rates and ratios and proportions. 90 feet per second is really 90 feet over 1 second. We have to think of it that way. And now I have to change my feet into miles and my seconds into hours. I'm going to start out with my feet. So I'm going to put feet on bottom here, miles on top. 1 mile is 5,280 feet. So now my feet have canceled out and are gone. But right now, technically my units would be miles per second. That's not what I want. I want miles per hour. So what unit do I need to get rid of next? The second. Where do I have to put it over here to make it cross cancel? On top. We're not used to putting things on top to cancel them out, but now we have to. Now I don't have seconds to hours, but I do have seconds to minutes. I know that 1 minute is 60 seconds. So the seconds cancel out. And then I can go from minutes to hours. 1 hour is 60 minutes. So now my minutes are gone. Now I do have miles per hour. That's what I want. So let's multiply things up and see what we get. We have 90 times 1 is just 90. Of course, that's 1 mile. Times 60 is 5,400. Times another 60 is that 324,000? That's miles. Over down here is just 1 times 5,280 times 1 times 1 hour. So it's 5,280 hours on bottom. So I have to divide that out now. 324,000 divided by 5,280 gives us 61.36. That'll be in miles per hour. So that's only 61.36 miles per hour. How many of you think I can throw that fast? Nobody wants to comment. If I warmed up really good, I probably still could. I probably only throw like 2 or 3 pitches at that before my arm started to hurt. I could probably still throw that fast. So we can do conversions with these dual units like this and make them work out. One that you might deal with, at some point, let's say that your car, you buy a car that's a foreign car and it's listed as, the gas mileage is listed as 6 kilometers per liter. Is that horrible gas mileage? Well, let's take a look. We're going to do 6 kilometers over 1 liter. And of course, what we want to convert that into is going to be miles per gallon, right? So we're going to get rid of the kilometers first. Kilometers on bottom here. Going into miles. If we look on page 576, we have 1 kilometer is what we're going to want equals 0.62 miles. So our kilometers have canceled out. Now I want to get rid of liters, so liters are going to go on bottom or on top, gallons on bottom. I want 1 gallon is 3.79 liters. So now my liters have canceled. So on bottom, I just have 1 times 1 times 1 gallon. So that's just 1 gallon. On top, I have 6 times 0.62 times 3.79 is 14.1, we'll round it to miles. So that's 14.1 miles per gallon. That's a 3/4 ton truck, pretty much. Not terrible. Some other conversions that we will run into. What does this symbol mean right here? Of course, FT is feet, but that is square feet. We know that 1 foot equals how many inches? Equals 12 inches. So is this going to be just 48 square inches? No, because we're not dealing with feet and inches. We're dealing with square feet and square inches. A square foot is literally a square that is 1 foot by 1 foot. Well, 1 foot is 12 inches by 12 inches. So 1 square foot is equal to 12 by 12, or 144 square inches. So when we're dealing with square units, units of area, our conversion factors have to be adjusted because we're dealing with 2 dimensions and not just 1. So to do this conversion, we would have 4 square feet over 1 square foot on bottom, 144 square inches on top. Canceling out gives us 576 square inches. Correct? Okay. Bless you. What if I had 42 square feet going into, actually let me change that just a little bit. Let's go 45 square feet, make it a little easier on us. Going into square yards. Well, again, we know that 1 yard is 3 feet, but this is square feet and square yards. A square yard is a square that is 1 yard by 1 yard, which is going to be 3 feet by 3 feet. So that 1 square yard is going to be 3 times 3, or 9 square feet. So if we convert, 45 square feet over 1, square feet going into square yards, 1 square yard is 9 square feet. You get 45 square yards over 9, which divides out to be 5 square yards. What you see happening here is when we're going into square units, or units of area, our conversion from our length gets squared. 3 squared is 9. 12 squared is 144, which is what we converted by for feet to inches. So with that in mind, what if I have or 3,456, I should say, cubic inches, and I want to convert that into cubic feet. We know that 1 foot equals 12 inches. When we were dealing with square feet and square inches, we squared the 12 to get our conversion factor. But now it's not squared feet and square inches, it's cubic feet and cubic inches. What do you think we're going to do to our conversion factor? Perfect. 12 cubed, or 12 times 12 times 12, which is 1,728. The reason for that is 1 cubic foot is 1 foot by 1 foot by 1 foot, which would be 12 inches by 12 inches by 12 inches. So 1 cubic foot equals 1,728 cubic inches. So in our conversion over here, 3,456 cubic inches over 1. Cubic inches are going to go on bottom, which is the 1728. 1 cubic foot on top. Cubic inches cancel out. Get 3,456 cubic feet over 1728, which divides out to be 2 cubic feet. What do you think? Not horrible? So what if we have metric units? When we converted metric units, every time we moved a spot on the chart, the decimal point moved 1 spot. That's because moving 1 spot on the chart was either multiplying or dividing by 10. So it moves the decimal point 1 spot. .7 millimeters equals how many centimeters? Well, to get from millimeters to centimeters, we go 1 spot to the left, don't we? So to move my decimal point, I have to go 1 spot to the left. That becomes 4.27 centimeters. Anybody have any questions on how we're moving that decimal point when we do our metric conversions? Okay. So now here's the question. What if that were, instead of 42.7 millimeters, it was 42.7 millimeters squared, converting into centimeters squared? Well, we're still moving millimeters to centimeters. It's still only one position on the chart, but it's squared, which means, if you think about it, it's 1 centimeter by 1 centimeter, and 1 centimeter is 10 millimeters. So 10 millimeters by 10 millimeters, which is going to be what? 1 square centimeter is 100 square millimeters. So now every spot on the chart is not multiplying or dividing by 10, it's multiplying or dividing by 10 squared, which is 100. In other words, each spot on the chart is how many decimal places? 2 decimal places. So we're moving 1 spot to the left on the chart. My decimal point has to go 2 spots to the left. So this becomes 0.427 centimeters squared. What if this is 42.7 millimeters, bless you, millimeters cubed, going to centimeters cubed? Well, now instead of being 2 decimal places for every spot on the chart, it's going to be 3 decimal places because it's 10 by 10 by 10, or 1,000. So we're still moving 1 spot to the left on the chart. My decimal point has to go 1, 2. I'm out of places, so I add a 0 to go 3 decimal places. So 0.0427 centimeters cubed. So let's say I have 0.083 meters squared. I'm going into centimeters squared. How many spots on the chart am I moving to get from meters to centimeters? 2 spots to the right. Am I going to move the decimal point 2 spots? Careful. Because it's not meters and centimeters, it's meters squared, right? Since it's squared, each position on the chart is 2 decimal places. So 2 spots on the chart is going to be 2 times 2 or 4 decimal places. 1, 2, 3, add a 0 to make it 4. That is 830. Make that a little illegible. So I have 0.000073 meters cubed going into millimeters cubed. Now meters to millimeters is 3 spots to the right on the chart. But now how many decimal places is each spot on the chart going to be? Yeah, we have to move 6. Each spot, well not 6, each spot on the chart is going to be 3 decimal places, right? Because it's cubed, right? So 3 spots on the chart becomes 3 times 3 or 9 decimal places. So you go 1, 2, 3, 4, 5, 6, and we have to add zeros, 7, 8, 9. So that's 73,000 millimeters cubed. So those conversions can get a little tricky. Let's say we have a conversion like this where we have, oh, let's see here. .2 grams per cubic millimeter. We want to know what that's going to be in kilograms per cubic centimeter. So we set this up as 4.2 grams over 1 cubic millimeter. Now we haven't done conversions with metrics, dual units like this. We did it with just standard, you know, the feet to inches and stuff. Here, what I'm going to do is I'm going to do this just a little bit differently. If I'm going from grams to kilograms, I'm going 3 spots to the left on the chart. So I'm just going to move my decimal point 3 spots to the left. This is 0.0042 kilograms. 1 millimeter cubed, if I'm going from millimeters to centimeters on the chart, that's 1 spot to the left, but it's cubed, so I have to go 3 decimal places. So I go 1, 2, 3, so that's 0.001. And I just divide it out. 0.0042 divided by 0.001. Is 4.2 kilograms per centimeter cubed. What if you have something listed as .48 ounces per square inch? And we want to know what that's going to be in pounds per square foot. So we will set this up, 48 ounces over 1 square inch. Now in the metric, we just moved the decimal places. We didn't need to do conversion factors. Here, we're going to have to do our conversion factors. So let's get rid of ounces first. We'll put ounces on bottom so they cancel out. What's going to have to go on top? What are we going to try to change ounces into? Pounds. So pounds goes on top. What's the relationship between ounces and pounds? 1 pound equals 16 ounces. Good. So there the ounces will cancel out. Now we're going to get rid of square inches. Where's it going to go? square inches will have to go on top. So on bottom will be square feet. You got it. So 1 square foot is 144 square inches. So the square inches are gone. So we have 48 times 1 times 144. 6912. And the only units left on top are pounds. On bottom, 1 times 16 times 1 is 16, and that is square feet. So divide the 6912 by 16 gives us 432. That is pounds per square foot. What do you think? I think that's a good spot for us to take our break. It's 10:04. Let's come back at 10:14.